Hello and welcome to another video. Today I want to talk about the ultrasonic sensor, the HCSR04 sensor. This is the ultrasonic sensor. I have an actual version of this with me. It's right here. The key idea that we want to talk about is what does this sensor do? How does it work? How can we code and get our items of interest basically from this? Now this sensor is using sound waves, and the sound waves are burst onto an obstacle that is in front of it, and then they reflect and bounce back off from the obstacle and are received by this sensor. And it tells you the distance or how far away the obstacle is from the sensor. Okay, so that is the purpose of this. It tells you how far away an object is, how far away an obstacle is from the sensor. Now, how does it function? Let's have a quick look at this. I'm using a last minute engineer's guide here. I'll put the link for this guide in the description of this video also. It uses ultrasound, and these are high frequencies. They're greater than 20 kilohertz. More specifically, if you look at the technical specs of this sensor, it operates at 5 volts, so we could always use 5 volts from the Arduino itself, right? So we have a 5-volt output right here on the Arduino, so we could use this 5 volts, and yeah, there it is. So you could use this 5 volts to basically power up the sensor, and I've connected the other pin on the ground also. Notice it has 4 pins that we want to work with. But before I go to the pin layout, I just want to also tell you that you're looking at a 15-degree measuring angle, and you're looking at a maximum range of 4 meters. All right, so that's pretty decent. Let's look at the pin layout. Yeah, so VCC 5 volts. So my orange jumper cable 5 volts is powering this up. I'm using this brown jumper cable as a ground, so that's that. And then there's trigger and echo, right? So these are the other 2 pins that would need to be set up, and I'm setting this up at pin 8 and pin 9, right? So trigger and echo at pin 8 and pin 9. This is what I'm doing in the code also. Pin 8 and pin 9. The reason I use const here is because then this variable becomes a read-only, cannot be changed throughout the code. And these are 8 and 9 are integers, but these are my pins on the board, but they are numbers, right? So I would define them as integers. I've got duration and distance also set up. Now, distance is an integer, I know that, but duration, what is the duration? Duration is the time it takes for the sound wave to travel from the sensor, hit the obstacle, and come back to the sensor. So that's the duration, and this could be a big number. So whenever we're dealing with big numbers, we use the long data type. This is 8 bytes, so it helps us store bigger numbers rather than using just int. From the last video, the structure is pretty much the same for this sketch. There's a setup, and then there's a loop functions. These are the 2 functions that we have in our sketch. The setup function is setting the pin modes for trigger and echo. We already defined them 8 and 9 on the board. Trigger is the output because you're sending out sound bursts from the sensor, so it's got to be defined as an output. And then you receive the sound waves after hitting the obstacle, and they come into the sensor, so it should be an input. So that's why we have trigger and echo. Yeah, we've initialized the serial also, 9600 baud rate, to print out and see what distances we get. The key idea here then is this is something very specific to the sensor. It's how it works. I would like to take you to this, right? So when you turn on the trigger, so the first 2 lines are just setting up and ensuring that you're clearing out the trigger pin. So it's setting a low voltage level, right? And then for 2 microseconds, and then you set the trigger pin high and keep it high for 10 microseconds, and then make it low, right? So this is the part basically which is implementing this triangle, a rectangular wave, right? So this rectangular wave, 10 microseconds, this is being implemented here in these 3 lines of code. You set it high for 10 microseconds and then set it low. So you do this for the trigger pin, and this gives the sensor a signal to transmit bursts of ultrasonic waves, and these are 8 to 10 bursts of ultrasonic wave, which then go hit an obstacle, and then the echo pin is waiting to receive any reflections that bounce off from the obstacle, right? And for it to start listening, we set the echo pin to high. So that's what's happening. The first two lines here, these are ensuring that the trigger pin is cleared out and it's at a low level. Then we set it to high and low. So that's how this is working. Um, the other idea here is this formula. What is this formula? So how do we really find out how far away an obstacle is? Notice the bursts are going in, hitting the obstacle, coming back. One of them is sending the burst and the other is receiving it. So the sound wave has actually traveled twice the distance. The obstacle is far away, maybe x centimeters, but the sound wave has traveled 2x centimeters. So because it's traveled twice the distance, we divide it by 2. That gives us the accurate number. We also convert the speed of sound into centimeters per microsecond. So speed of sound is taken as 340 meters per second. You could see whatever is accurate, but you then convert it to centimeters per microsecond and then becomes 0.034. The duration of this sound wave travel is in microseconds. So this microsecond cancel out with microsecond and the speed of sound. Resultantly, we have the distance in centimeters. So whatever we see here is in centimeters. Right? The distance speed formula is very simple. Distance is speed in time. This is something we know. The calculations and more explanation are on this link also will be in the description of the video. What I want to get down into is I have my Arduino connected. I want to burn this SketchUp on the board and then show you what the distance looks like, and then we'll make one small improvisation here. Let's turn on the serial monitor, and yes, we do see that the distance is being shown up. If I put my hand on top of it, I should expect the distance to go down, and it does, right? But I want to do a quick test, so to speak, to see how accurate these readings are, just to make it a point whether or not this could be reliably used. So I'm going to go ahead, show you the scale, 0 to 6 centimeters. Okay, let's keep it straight. And then let's position our sensor, perhaps here, right? Make sure it's aligned with it. It's 90 degrees to the scale, right? And this is what I'm going to do. I'm going to bring an obstacle in front of it, and you have the scale shown up, and you could see how accurate this really is. Do we really see the equivalent centimeters, right? Let's go ahead and try this out. Let me bring this right in front of the, it's actually a board, probably not visible right now, but as I will bring it closer, you'll see it does become visible. So let me bring it to the 6 centimeter mark. Okay, so this is a box. It's close to the 6 centimeter, as you could see, and we get pretty much an accurate reading, probably off by a centimeter or half centimeter, some rounding off errors maybe, or maybe the angle is not so 90. Notice as I move this angle, the readings seem to change, right? So the sound waves bounce off and they don't quite, they're not quite received well on the echo, right? Or maybe I should put my obstacle right like this, make sure it is completely bounced off it. Okay, so 5 centimeters, it is pretty much accurate. 4 centimeters, it is pretty much accurate, and down to 3 centimeters, yeah, it is pretty much accurate. So you could see that in terms of accuracy, this sensor is pretty nice. Down to the centimeters, it is nice, but the key thing that we want to take care of is whenever we position it, it needs to be uh, perpendicular. It needs to be set up nicely. Otherwise, if there's an angle introduced, sound waves seem to go off and then they might not be received in as nicely. So that could give away with the readings. Well, that is pretty much it. I just want to add one last thing to this, and that is, let me plug in the charger, one moment. Yeah, okay, so one last idea that I want to talk about before we end this is the use of functions. Notice there's a lot of clutter here and you might not be interested in. You might be doing or implementing any other logic, so you might not be interested in writing this code right here as it is, right? So, and obviously we want to reuse the code in different places at times. So one of the things we could do is we could put all of this code into what's called a function, right? And these are the built-in functions. What we could do is define one of our own. So we could go ahead and define maybe, let's just call it distance distance function, right? And paste the entire clutter of code, which we may not need, right? I mean, we need it in every loop, but we might not want to just show it in the loop as it is, because we might be interested in writing our own logic in this loop. So it helps it look nice, and also enhances reusability. So we've got distance func, and we've got the entire thing set up here. That's okay. uh, and then we could call this function in loop, and that's about it. We could say distance func, and that's how we could simply call this function. So a few things that we might want to keep into we might want to remember here. uh, okay, I might not be interested in serial printing right here. I might want to print them here, but I want to return something from this function. I want to return the distance, and that is an integer. So notice what I've done. Let me just take this out and print this here and call this as dist. Okay, I've done a bunch of things here, but I want to show you what this is, and also dist. Okay, so I've defined a function, distance function. It's going to return me an integer because I'm returning an integer distance. So that's something I get every time this function is called. How do I call this function? I simply call it by its name, make sure the round brackets are there, and whatever the answer is being returned, it gets stored in dist, which is something that I print. Okay, so let's go ahead and burn this and see what we get. It should ideally give you the same thing, right? I don't know if we could. Yeah, so it gives us the same thing. But now the clutter is kind of cleared in my loop function, and I could go ahead and work with some logic, right? For example, if dist is say less than 10, and I'll put this in round brackets, then maybe go ahead and do a print less than 10. Okay, uh, print line new, so it shows up on the new line, and else you could print that it is greater than 10. Okay, so now I might not even, you know, get the distance, and based on what the distance is, make sure what our prints look like. Okay, so it is greater than 10. Oh, there's a delay in my video feed, but that's okay. I've put my hand on top of the sensor, it's less than 10. I remove my hand, it's far away. So you could base your logic on any. Yeah, there's a delay in the video, but anyways, you could base your logic on what you get, and you can access the same lines of code through a function. So that eliminates the clutter in the code in the loop. And in some applications, in some implementations, doing this functionalizing basically your lines of code helps to reuse them at a different place. In this case, we're not really bothered because we're running this in a loop. It's happening again and again, so that's okay. But in other cases where you might want to call some things again and again, it helps to functionalize. So this is one example of functionalizing the code and working with the ultrasonic sensor. I'll see you in the next one. If you have any comments, feel free to drop them down. Thank you.